Hi guys, I'm Amanda, and today we'll be going over differentiation methods and theory. We'll be applying implicit differentiation, then using whatever we find from that in order to get equations for tangent and normal lines. So A asks us to find dy dx in terms of x and y if 3x squared minus 2xy plus 5y squared equals 13. So normally when we're asked to differentiate, we're given a function written as y equals something written explicitly in terms of x. And with those types of functions, we just find the derivative with our normal derivative rules, like our power rule, product rule, constant sum, difference rule, all that. But when a function isn't written as y equals some x, we have to use implicit differentiation. And this is kind of another way of using the chain rule, allowing us to differentiate functions within functions. On the side, this is just a brief visualization of how we're using the chain rule in implicit differentiation. Now B asks us to write an equation of the normal line at the point 2, 1. So now we'll be moving on into the actual problem solving. Here I just like to rewrite the equation just so I know what I'm dealing with. Now I put everything in parentheses just for simplification. Here I'm doing some actual differentiation. So here we're using the power rule in 3x squared, bringing the 2 down, multiplying that by 3, leaving the x and taking the 2 minus 1, and then next we're doing the power rule, taking the 2x first. When we differentiate 2, that becomes a 0, and leave the x alone, add that to 2, and then the derivative of x is, of course, 1. And that whole thing is the derivative of 2x. And then we're continuing with the product rule, leaving the y, and then adding that to 2x alone times 1 times dy dx, which is, of course, the derivative of y. Now we're moving on to 5y squared, using the power rule again, as we saw in the 3x squared term, except now, since we have a y, we have to implicitly differentiate, which is why we're tagging on that dy dx. And then, of course, we know using the constant rule that the derivative of 13 is just 0. And now, of course, we're simplifying, and simplifying even more. And now, of course, we distribute the negative 1 to the 2y and 2x dy dx, so that becomes a negative 2y minus 2x dy dx. At this point, we realize we have to get dy dx on one side alone and all the other terms on the other side. So to do this, we subtract 6x from both sides and add 2y to both sides. Now we can take out the dy dx by factoring from both terms. Now finally, to completely isolate the dy dx, we can divide both sides by negative 2x plus 10y. Next, we can multiply both the numerator and denominator by 1/2 because it's basically just multiplying by 1. Then we get our final answer of dy dx equals negative 3x plus y over negative x plus 5y. Next, we can move on to part B, which asks us to write an equation of the normal line at the point 2, 1. Now we know the normal line is the line that is perpendicular to the tangent line at the point of tangency, and therefore is a negative reciprocal of the tangent line. We also know that if the slope of the tangent line is f prime of x, then the slope of the normal line must be negative 1 over f prime of x, because it's the negative reciprocal of the tangent line. Here we're just evaluating dy over dx, also known as f prime of x, also known as the slope of the tangent line at 2, 1, by plugging in 2 for x and 1 for y. Now we plug our value into our equation for the normal line, which is negative 1 over f prime of x, so negative 1 over negative 5 over 3. Now the equation for a line is y equals mx plus b, and in our case, y is 1, m is 3 over 5, and x is 2. With this, we solve for b. Now after we solve for the b value, we simply plug that into the normal line equation as well as the m value. Then we get y equals 3/5 x minus 1/5. Now there is another approach we can take, and that's going along with the trusty tangent line equation, which reads y minus f of a equals f prime of a times x minus a. But in our case, we'd replace the f prime of a with negative 1 over f prime of a, because we're looking for the normal line. So when we plug in all our values, we basically get y minus 1 equals 3/5 x minus. When you simplify that, we get the same answer as we did before, which is y equals 3/5 x minus 1/5. And that is our equation for the normal line at the point 2, 1.